electric potential. It is the symbol V. So this is generally this electric potential. This is another method. With the help of this, another method. This is another method to calculate electric field E. This is another method to calculate electric field E. Now we will define what is this electrical potential. Suppose some field exists in free space. Some field exists. Like this, field exists. Suppose if I want to move from a particular point A, if I want to move a charge is Q exists in the field, a charge Q exists in the field at point A. Suppose if I want to move this point charge from point A to another point B, to another point B, I want to move. Suppose this is origin. That is, I have to move the charge against the field. This is field. I have to move the charge against the field. So this is electric field. Electric field. I want to move a point charge from A to B. That is, I have to move the charge against the field. Suppose this is a radius vector RA. This is a radius vector RB. Radius vector RB. So if I want to move the point charge from A to B, I have to do some work. I have to do some work. So the work done, therefore, work done in displacing the point charge by a distance dl, that is, I am moving a small distance dl. So the work done in moving the charge by a small distance dl is given by small dw is equal to minus f into dl, where f is force, on q, force on q. So force on q, f is equal to, here the field is electric field, q into E, f is equal to q into E. Here the negative sign indicates that the work done by some external agent, or we are doing, some external agent is doing the work to move the charge against the electric field. Here I am considering positive charge. So I am moving the charge against the field. So some external agent is needed to move the charge. So that's why here this negative sign indicates that the work is being done by an external agent. Work is being done by an external agent or against the field. Simply we can say that against the field. Therefore, total work done, this is also known as potential energy, total work done required in moving Q from A to B is, so total work done is total work W is equal to integration over this value. So integration over minus A to B F dot dl. Therefore work done, total work done is minus integration A to B F is equal to QE dot dl. This is equal to W is equal to minus Q integration A to B E dot dl. E dot dl. W by Q is equal to minus integration A to B E dot dl. So this W by Q ratio has some particular name, particular meaning. That is, this is known as potential energy per unit charge. Potential energy, this is known as potential energy. I am dividing with Q. So potential energy per unit charge. That is nothing but I am moving a unit charge. So potential energy for unit charge. So this quantity is represented by VAB, potential difference. This is represented as potential difference between point A and B. So VAB is equal to W by Q minus integration A to B E dot dl. So suppose when determining this VAB, A is the initial point, B is the final point. Suppose example, this is X, Y, Z, the electric field, this is origin, this is P, resistance R. Suppose QE is located at this particular origin. And what is the electric field? Electric field is given by Q by 4 pi epsilon naught R square AR bar, due to this key. So in this electric field, if you want to move from A to B, so then VAB is given by minus integration, the figure already we shown, RA, that is A to B, RA to RB, Q by 4 pi epsilon R square AR bar. That is here point A is at 0. This is point B. So 0 to RB you have to move. So if you simplify this integration, general we get the potential VAB or the potential is given by, because here one point I am considering as origin, Q by 4 pi epsilon R. V is equal to Q by 4 pi epsilon R. That is the potential at this particular point P. Because here the distance is IA is equal to 0. B is at R. So you have to integrate in the range of integration 0 to R. So if you simplify this, you will get the voltage, the potential at point P is V. Q by 4 pi epsilon naught R, because the initial point is at 0. So the potential at any point is the potential difference between that point and a reference point at which the potential is 0. Here at the origin the potential is 0. So potential we can define as the potential at any point is the potential difference between that point and a chosen point or a reference point at which potential is 0. So that is, electric field intensity is inversely proportional to 1 by r square. Voltage is potential is proportional to 1 by r. So this is one of the important statement we can conclude. We will work out a simple problem to understand this potential concept. The problem is, two point charges -4 microcoulomb and 5 microcoulomb are located at 2, -1, 3 and 0, 4, -2 respectively. What is the potential at 1, 0, 1? Assume 0 potential at infinity. 0 potential at infinity. So the solution to this problem is very simple. 2 point charges, this is Q, -4 microcoulomb, Q1, Q2, 5 microcoulomb are located here. This point is at 2, -1, 3, 0, 4, -2. Then what is the potential at a particular point? 1, 0, 1. So I want to calculate the potential at this particular point. So the distance is this. Due to this, the distance is this due to Q2. This is R1. This is R2. Assume 0 potential at infinity. We know that here we are having two charges. We are applying superposition theorem. Potential is equal to V1 plus V2. V1 is given by Q1 by 4 pi epsilon naught R, where R is the distance, R1. So R1 I am calculating. R1 is nothing but, this is the distance between these two. So R1 is given by, so first of all calculate R1 bar, radius vector. 1, 0, 1 minus 2, -1, 3. That is given by -1, 1, -2. So the magnitude of R1 bar is square root of 1 plus 1 plus 4, that is square root of 6. Similarly, V2 is equal to Q2 by 4 pi epsilon naught R2. So R2 bar is given by 1, 0, 1 minus 0, 4, -2. That is equal to 1, -4, 3. So modulus of R2 bar is square root of 1 plus 16 plus 9. That is square root of 26. Therefore total potential V is 1 by 4 pi epsilon naught common. So 1 by 4 pi epsilon naught if you take common, Q1 -4 microcoulomb. So -4 into 10 power -6 by R1, magnitude of R1, square root of 6, minus 5 into 10 power -6 by square root of 26. So if you simplify this, you will get approximately minus 5.872 kilovolts. So that is the potential at that particular point. Potential at that particular point. So like this you can calculate potential. Next we will see relationship between electric field and potential. Relationship between E and V. One statement is the potential difference between 2 points A and B is independent of path taken. That is, suppose here I am coming from A to B, the potential difference is VAB. Suppose I am coming like this, V to B to A, the potential difference is VBA. How we can relate is VBA is equal to minus VAB. Therefore, VBA plus VAB is equal to 0. But how I can define potential? That is, now what happens? VAB again B to A. So this implies, but we can define VAB as the potential we can define as integration minus E dot dl. Therefore, the closed line E dot dl is equal to 0. Closed contour C, E dot dl is equal to 0. But we know that by using Stokes theorem, I can integrate closed line to open surface. So integration over closed line E dot dl is equal to integration over S del cross E dot ds. So for this case that is equal to 0. So this particular equation shows that the line integral of E along a closed path is 0. So physically this implies that the resultant work done is 0. In moving a charge along a closed path. The resultant work done is 0. That implies the resultant work done in moving a charge along a closed path is 0. So this statement. So that implies what? Del cross E is equal to 0. That is, there is no rotational field at all. The electric field is not rotating at all in free space. That is, the circulation of the field is 0. The circulation of the electric field is 0. So del cross E is equal to 0. So this is second Maxwell's equation. For static case. This is static case, that is static fields we are considering for static case. Second Maxwell's equation for static case. This is also in differential form or point form. This is integral form of second Maxwell's equation. Del cross E is equal to 0. So we also know that del cross E is equal to 0. Circulation of the field is 0. That is, the electric field is having the property, it will not rotate. Electric field will not rotate. This is also known as conservative field. It is also known as del cross E is 0 means irrotational. Irrotational is also called as conservative field. So like this we can derive second Maxwell's equation. Which is del cross E is equal to 0. So generally we can write that V is equal to potential is equal to minus E dot dl. So here if you observe this particular relation in the starting, that is in the beginning of our discussions, we say that this is a voltage. V is nothing but voltage. So voltage is nothing but integrated effect of electric field. Integrated effect of electric field. That's why the circuit theory and field they are related. So this is the best example. So V is equal to minus E dot dl. So voltage is nothing but integrated effect of electric field. So V is equal to minus integration E dot dl. But E I can write Ex Ax cap plus Ey Ay cap plus Ez Az cap. Dl differential length dx Ax plus dy Ay plus dz Az. Therefore E dot dl E dot dl is Ex dx plus Ey dy plus Ez dz. But what I am doing, I am taking differentiation dv. So if I take differentiation on both sides, integration vanishes. That is minus E dot dl. Minus E dot dl. So that is equal to minus Ex dx minus Ey dy minus Ez dz. But how I can define dv? dv I can write dv is equal to dou by dou x of v dx, dou by dou y of v dou y plus dou by dou z of v dz. This is the differentiation property, writing a differential quantity dv. So compare the two equations. Compare both sides. So if you compare both sides, what are you getting? Ex is equal to minus dou v by dou x. Ey is equal to minus dou v by dou y. Ez is equal to minus dou v by dou z. So this implies E is equal to minus del v. E is equal to minus del v. E is equal to minus del v. So electric field is nothing but gradient of potential. Electric field is nothing but gradient of V. So electric field intensity is gradient of V. Gradient of V. So what is the meaning of gradient? Gradient means the spatial variation of the scalar quantity. The distribution of the variation of the quantity in free space. So the variation of the potential with respect to space is nothing but a electric field. Here the negative sign shows that the direction of E is opposite to the direction in which the potential increases. One more thing is, suppose if you take curl del cross E, that is del cross minus del V. But del cross E is equal to 0 for static cases. Therefore, del cross del V is also equal to 0. That is the curl of gradient. The curl of gradient. Curl of gradient. Gradient of a scalar. Curl of gradient of a scalar is 0. Curl of gradient of a scalar is 0. So this is one of the important relation, which is E is equal to minus del V.